time to learn a little something about rotaries, right? Here's the housing, here's the iron, here's the rotor, here's the apex seal. Intake port, exhaust port, trailing hole, leading hole, and this applies to pretty much all rotary engines modeled base, okay? Now, do the math. This is an RX-8 apex seal, but it's very similar to an RX-71. The only difference is that it's much shorter than an RX-71. An RX-71 is much taller. I think it's about this tall. And you can actually see right here the difference. Right here. Throw the seal in here. Because this is an RX-7 rotor. You can physically see that it's kind of hard to get in there. Let's force it in there. I can't really force it in there, but you can essentially see that there's room to spare. So that's how tall an RX-71 is. Anyways, moving on to the point. Okay. 2 millimeters. Okay. Trailing hole, 4.5 millimeters wide. Leading, 12.5 millimeters wide. And if you see another thing, see where the threads end? That's where the spark plug face usually sits at. And there's a little bit of dead volume right there. There's about 5 millimeters of dead volume, and it's the same thing on the trailing hole. Both have 5 millimeters of dead volume between the actual face of the spark plug and the engine itself, right here where the housing surfaces on both these, right? Remember, 2 millimeters. Okay. Now let's take the rotor. Let's go through the 4 stages of combustion in a rotary, right? Now, let's focus on this face, but you gotta remember that it's also happening on the 2 other faces at the same time. Okay? Now let's start with this face. Right? You're starting intake, right? Intake port opens. Right? Now fully open. It is fully open. Now, as it's fully open, then the other side of the rotor will start to close it. And here's something that gets interesting, right? Then right around here, rotor is completely, intake is completely sealed off, right around there, sealed off from the intake, right? Now, it's time to start building compression. Now you have that closed, right? As you start building compression, remember that seal that I told you about? It's 2 millimeters. Leading hole, 12.5, 5 millimeters of dead space right there. Guess what happens? As soon as that seal crosses over that hole, as it's building compression, remember, it just started building compression. As it's building compression, you see right here, that is the moment that when the seal crosses over, it causes both the compression and fuel to leak through. Now, those measurements may be tiny, 2 millimeters, 5 millimeters, 12.5 millimeters. You have to understand that this thing is moving between 180 to 3,000 times a minute. And the problem is the fuel. We'll talk about the fuel first, right? The fuel is being, on average, wasted so much so that per hour, and this is using an RX-8 engine, per hour you're wasting more fuel than this bottle can hold water, right? That fuel is just getting straight sent to exhaust, and that is average. That is not a specific RPM, compression ratio, but this is for an RX-8 engine 10-to-1. But essentially, you're wasting this plus some change of fuel that is just getting wasted in exhaust that you could use to turn the engine to move the car, right? Now, you have that leak, right? It also, not only leaking fuel, you're also leaking compression. When you leak compression, your dynamic compression ratio drops, but you can also change this with how fast you spin the rotor, right? Now at low RPMs, when this is at idle, which is around 180 RPM, you're leaking most of the compression. Usually 10-to-1 translates into 7 to 7.5, right? Between 180 to maybe 500 RPM, right? It's pretty low dynamically, right? As you climb, and we're talking about each shaft now, let's say about 4,000. Now this is moving a little bit closer to 1,000, right? The compression starts going up because the time that it takes for the seal to cross the hole gets shorter, and now that's less time for the compression to leak out. Now, the only time you actually get the compression ratio of a rotor, let's say 10-to-1, is pretty much at peak red line, right? So that's when you get your actual, okay, they weren't lying, it's just actually at, you know, peak RPM, which is why these engines have to make power at peak RPM. But guess what this hurts? Low end torque. It hurts idle stability, especially when you start bridge porting and porting engines and stuff like that. That's what that hurts. Now let's keep on moving with the rotor. So that's one issue, right? Now remember I said about the trailing, it's much smaller, 4.5, but you still have that 5 millimeter dead space. And this is 2, so you still have 2.5 millimeters of dead space essentially, right? Now here's one thing, right? Now remember, compression, right? And we're about to go, boom, right? Leading goes first, then trailing goes after, pushes the rotor. And guess what? Look what happens here. Look at this seal right here. When it crosses over, essentially, let's see, right around there, boom. Look at that. Now you have another leak, but you're not leaking fuel compression. Remember, this just fired, essentially. This is hot fuel, air, a lot of pressure, right? And then you also have to think about the pressure differences. This is only 80 to 120 psi. This is much higher, and heat as well. It's very hot. The difference between in temperature is insane between here. Thousands of degrees difference, right? Now guess what this does, right? Especially at high RPM where this is mostly affected. This pushes like a blowtorch, right? There's a lot of high heat and pressure. This pushes through that hole, and it pushes it right into the intake stroke essentially, because you see that? The intake is still open. So it's like internal EGR. And what this hurts the ability to run high compression and boost, right? That's why you don't see people with 10-to-1 compression rotaries, right? RX-8, right? That's why RX-8s have to be carefully tuned, right? People don't really boost them because of that reason, right? And you need a lot of cooling mods in order to cool the intake charge, right? But this is one reason, because now you're adding a ton of heat and pressure into the intake stroke essentially, right? And because you're adding all of that, right? Imagine like a high boosted engine with high compression. That can cause detonation. That can cause the rotor to spin backwards, which you don't want to do, right? Because now you're throwing that heat and pressure back into the intake stroke. This can, at high boost and RPM, this can kick back the rotor. And that's how you shatter an apex seal, right? Now I know what you're asking. There's got to be a way to fix this, right? Well, there is, right? And this is my good friend. His name is Renesis Revival on YouTube. Learned through all his videos for the past year, etc. Basically, threw in a reverse threaded sleeve for the leading and the trailing. And the sleeve hole itself, the actual hole on the other side, on the housing side, is smaller than the apex seal. It's about 1.8. And he makes variations that are 1.6 millimeters, 1.8 millimeter, depending on the kind of spark plug you use, right? And the spark plug you use specifically for this is you want to use a motorcycle spark plug, because they are built for tight tolerances, because motorcycle engines are tiny, right? That's why he uses a motorcycle plug. And they have modern materials, etc. We live in 2026. We don't live in 1985 anymore, okay? So essentially, because you have it smaller, you seal off the chambers completely from each other, right? Right now you don't have this leaking, compression and fuel leaking into the exhaust face, which gets shut out right there. And then from here you don't have extra heat and pressure being leaked in here, right? So you save fuel, you gain back your compression, you gain back low end torque, idle stability, and you gain back combustion control of the engine, because you don't have that pressure and heat being shot in there. Now I know what you're thinking too. 4.5 millimeter, 2 millimeter, 5 millimeter. If the rotor is moving so quickly at 9,000 RPM, why is this such a problem? Because the problem is not leaking, it's heat. You're pushing heat into the intake stroke, which should be cold. It's supposed to have cold air for a reason, because cold air is denser. You have more power with colder air, right? And especially with, if the bathtub is even more shallow, it can cause detonation easier, right? Which is why people are afraid of running 10-to-1 turbo engines, 9.7-to-1, right? Turbo engines with a lot of power and either pump gas or even methanol, right? It's too unsafe with the amount of boost that you're pushing, because the pressure difference, especially with a high boosted 13 Bs that are making 1300 horsepower, right? This is what, 180, 200, 120 psi of pressure right here. The boosted engine, shit, this is like 1500 psi to 2000 psi of pressure. So you have two areas with two pressure differences, and you have an opening in between them. Not only you have an opening, all that heat can escape through there. So you gain back your AFR authority and your combustion authority, which means that now it's possible to run high compression boost. One, you don't need to dump as much fuel for safety, and two, you don't have to worry about knock as much anymore, because you have sealed off that chamber from the other chamber. Now you're not adding that extra heat anymore, which means that you can advance the timing just a little bit more, right? A lot of people are focused on the add-ons of the leading, which is very good, but people don't realize how dangerous that trailing is. And even in itself, right, you can see that Mazda purposely made that one smaller, because, little history time, back in the 60s, Mazda made the hole the same size as the leading. And you know what that did? That caused backfires in the carburetor and an intake manifold, because it would have air, a lot of hot pressurized air being pushed back into the intake stroke, and it will blow up the carburetor. So Mazda purposely made it smaller so it wouldn't be as bad. But now, essentially in 2026, you're fixing that problem because of modern technology and spark plugs and all. You don't have to worry about carbon buildup, because that's another reason why they never made these the right size from the factory, because the carbon buildup. When you don't worry about that carbon buildup, I mean, you can have your cake and eat it too, essentially. So there you go. That's how you fix the rotary engine without having to reinvent it. It's pretty simple. That's it.